1. Scientists solve 50-year quantum mystery, wave-particle duality breakthrough. 2. New quantum formula explains wave-particle duality with 100% accuracy. 3. Harnessing wave-particle duality, a breakthrough in quantum imaging. 1. Scientists solve 50-year quantum mystery, wave-particle duality breakthrough. Wave or particle? Physicists solve a 50-year-old quantum mystery ****. In a remarkable breakthrough, a team from Stevens Institute of Technology has successfully utilized both the wave-like and particle-like characteristics of quantum entities to create an innovative imaging technique. For over a century, quantum mechanics has fundamentally altered our understanding of the universe, revealing a bizarre and often counterintuitive domain where particles can exhibit wave properties, and the act of observation can actually affect the results of experiments. Recently, researchers investigating this intriguing phenomenon, known as wave-particle duality, have devised methods to assess the extent to which a quantum object displays wave-like or particle-like behavior. These assessments have provided valuable insights into the conditions that lead quantum systems to oscillate between behaving like particles and acting like waves. In a study featured in Physical Review Research, the Stevens team has made a significant advancement by formulating a clear yet highly accurate equation that delineates the precise mathematical relationship between a quantum object's wave-like and particle-like attributes. Wave-particle duality is fundamental to quantum mechanics, states Xiaofeng Qian, the lead author of the paper and an assistant professor of physics at Stevens. For the past 50 years, researchers have sought to quantify wave-particle duality, but this is the first comprehensive framework that fully quantifies both wave-like and particle-like behaviors using optimal quantitative measures relevant at the quantum level. Breaking through previous model limitations. Earlier studies indicated that wave-like and particle-like characteristics could be represented as an inequality, where the total of an object's wave-like behaviors, like observable interference patterns, and particle-like behaviors, such as the predictability of its trajectory or position, is equal to or less than 1. This is crucial because it implies that if an object is entirely wave-like, it exhibits no particle-like traits, and vice versa, Qian clarifies. However, these models were incomplete as they could describe scenarios where an object's wave-like and particle-like behaviors increased simultaneously, which contradicts the actual exclusive relationship between these two behaviors. To address this, the authors introduced a new variable, the coherence of the quantum object. Coherence is a complex concept, but it essentially serves as a hidden descriptor of the potential for wave-like interference, Qian explains. The conventional measure of visibility indicates the extent of wave-ness that can be extracted. By quantifying and adjusting for coherence, along with the standard metrics for wave-ness and particle-ness, we discover that they sum to exactly 1. From inequality to precise calculation. This advancement allows for a much more precise calculation of both wave-ness and particle-ness. By measuring coherence within a system, it becomes feasible to determine a quantum object's level of wave-ness and particle-ness, not merely as less than 1, but as a specific value. The relationship between wave-ness and particle-ness can then be elegantly represented on a graph, forming a perfect quarter circle for a completely coherent system, and a flatter ellipse as coherence diminishes. In addition to enhancing our comprehension of fundamental physics, this breakthrough holds significant potential for applications in areas such as quantum information and quantum computing. To illustrate this, Qian's team applied their theory to a method known as quantum imaging with undetected photons, QIUP, where an object aperture is scanned using one of a pair of entangled photons. If the photon passes through without obstruction, coherence remains high. However, if it collides with the aperture's walls, coherence drops sharply. By measuring the wave-ness and particle-ness of the entangled partner photon, Qian's team could infer its coherence and thus outline the shape of the aperture. This demonstrates that the wave-ness and particle-ness of a quantum object can serve as a resource in quantum imaging, and potentially in various other quantum information or computational tasks, Qian remarks. Resilience against environmental noise. Remarkably, imaging capabilities persisted even as external factors, such as temperature fluctuations or vibrations, compromised the overall coherence of the quantum system. These factors impact both high coherence scenarios, where the photon traverses the aperture, and low coherence scenarios, where the photon interacts with the scanned object, allowing for the detection of differences in coherence between the two situations. The ellipse may become compressed, but we can still extract the necessary information about the object, Qian explains. Further investigation is essential, particularly to understand how wave-particle duality manifests in more intricate multipath quantum scenarios. The mathematics may appear straightforward, but we are far from fully unraveling the complexities of quantum mechanics, Qian states. there are still numerous frontiers left for us to explore. Reference **, Wave-particle duality ellipse and application in quantum imaging with undetected photons, by Powenkata Wada and Xiaofeng Qian, July 8, 2025, Physical Review Research. DOI 10.1103/DYG6, L19J. Stay updated *, don't miss out on groundbreaking discoveries, subscribe to the SciTech Daily newsletter. 2. New quantum formula explains wave-particle duality with 100% accuracy. A groundbreaking discovery in quantum physics. Imagine a breakthrough in quantum physics that not only clarifies the complex relationship between wave-like and particle-like behaviors of quantum objects but does so with perfect accuracy. This is exactly what researchers at the Stevens Institute of Technology achieved as of July 8, 2025. In a remarkable study published in Physical Review Research, they unveiled a comprehensive mathematical framework that decisively connects these two fundamental aspects, resolving a long-standing dilemma that has puzzled scientists for over a century. Their innovative formula reveals that the contributions of wave-ness and particle-ness combine seamlessly to equal 1 when integrating the concept of quantum coherence, a vital factor related to the potential for wave interference. Consequently, this represents a significant leap forward from earlier models, which permitted an increase in both behaviors independently. This pivotal advancement holds promising implications for realms such as quantum computing and quantum imaging, underscoring the researchers' capabilities by demonstrating coherent quantum imaging with undetected photons. It maintained exceptional image clarity despite disturbances in the system, paving the way for groundbreaking technologies that require precise control over quantum states. Understanding wave-particle duality, a century in the making. The principle of wave-particle duality posits an intriguing idea: quantum objects do not strictly behave as either waves or particles, instead, they embody a blend of both. The recent investigations conducted at Stevens Institute have refined our grasp of this duality by formulating a more exact mathematical representation. Earlier theory suggested that the wave-like and particle-like attributes could not surpass a total of 1, yet they fell short in addressing conditions where both traits might elevate simultaneously. By integrating coherence, essentially a measurable potential for wave interference, the scientists unveiled a straightforward relationship: the sum of wave-ness and particle-ness is always 1. This breakthrough not only offers clarity but also deeply enhances our ability to calculate these properties accurately. Visually interpreted, this relationship reveals itself as an elegant curve, a perfect quarter circle indicative of fully coherent systems, which transitions into a more flattened ellipse as coherence dwindles. This newfound precision in determining wave-ness and particle-ness could revolutionize various applications in quantum information technology and computational fields. Practical application through quantum imaging. The Stevens team skillfully demonstrated their refined understanding through a technique known as quantum imaging with undetected photons, QIUP. By employing entangled photon pairs, they scanned an aperture using one photon while analyzing the coherence of its entangled twin. This innovative approach successfully mapped the shape of the aperture, showcasing the potential of utilizing both wave-like and particle-like properties as valuable resources in quantum imaging. Perhaps even more fascinating is that this imaging technique remained functional, despite disruptions caused by external factors such as temperature fluctuations and vibrations. Interestingly, these influence both high and low coherence situations alike, allowing for detectable nuances in coherence and enabling ongoing information retrieval. Notably, even with a reduction in the dimensions of the ellipse representing coherence, the integrity of the object's information remained intact. The pivotal role of quantum coherence. The introduction of coherence as a quantifiable variable significantly enhances existing models' efficacy. The summation of wave-like and particle-like behaviors is elegantly positioned as 1, thanks to the researchers' inclusion of quantum coherence. This not only moves the understanding from probabilistic reasoning to deterministic calculations, but also elucidates a clear, reciprocal link between the two characteristics. In quantum imaging, this advancement manifests its practical relevance spectacularly. By adeptly measuring the coherence of one of the entangled photons, the study illustrated how quantum properties can be harnessed for image construction and reconstruction, an approach unviable through traditional detection methods. This means that the concept of coherence transforms into a resource loaded with information, making it exceedingly beneficial for imaging efforts, especially in complex scenarios where conventional techniques may not suffice. The resilience of this imaging method against environmental disruptions underscores its practical applications in real-world settings. Despite conditions that would typically diminish overall system coherence, the technique continues to operate effectively. The adjustment in the wave-particle duality ellipse, signifying varying levels of coherence, does not correlate with a straightforward loss of information, but rather presents a change in signal quality that can be managed through smart data processing strategies. #Future insights and complex systems. The exciting developments in understanding wave-particle duality are just the beginning. There lies a tremendous opportunity for future research. Scholars will need to delve deeper into these principles, particularly within more intricate multipath quantum scenarios where several pathways interact simultaneously. This complexity is permanently present in many practical applications, posing substantial challenges for both theoretical modeling and empirical validation. Grasping how coherence is either preserved or compromised in such contexts will be crucial for the advancement of functional quantum technologies. A particularly promising research avenue includes the prospect of actively manipulating coherence to amplify quantum imaging effectiveness. The ability to proactively adjust coherence, potentially through tailored electromagnetic fields, could unlock a variety of new imaging techniques and functionalities. Moreover, there's a vital need to further explore the relationship between coherence and image resolution. A detailed understanding of how coherence impacts or even enhances resolution in QIUP and other imaging methods will be essential for evolving state-of-the-art imaging systems. Overall, the potential scalability of these findings, to encompass larger and more complex imaging scenarios, will be vital in determining their real-world applicability beyond laboratory settings. As researchers keep exploring the interplay between coherence, entangled photon quality, and detection efficiency, the prospects for manipulating coherence in quantum imaging systems could herald a new era of innovative imaging modalities, significantly more advanced than what classical methods can achieve. #Join the conversation. Intrigued by these pioneering insights in quantum mechanics? It's fascinating to consider how these developments could change our understanding of the universe. What do you think about the implications of refining wave-particle duality through coherence? Are there other aspects of quantum mechanics you believe deserve focus in future research? Feel free to share your thoughts or disagreements in the comments below. 3. Harnessing wave-particle duality, a breakthrough in quantum imaging. Unlocking the mysteries of quantum imaging, a revolutionary study. Imagine a world where the very fabric of reality behaves in ways that defy our traditional understanding. This is the realm of quantum mechanics, a field that has fascinated scientists for over a century. A recent groundbreaking study from the Stevens Institute of Technology has taken a significant step forward by developing a formula that accurately measures the dual nature of quantum objects, both their wave-like and particle-like properties. This advancement paves the way for innovative imaging techniques that utilize undetected photons. For many years, quantum mechanics has revealed a universe that is often stranger than fiction, where particles can act as waves and change their behavior simply by being observed. The latest research from Stevens Institute not only enhances our grasp of the fundamental principle of wave-particle duality but also applies this understanding to create a new imaging method. Published in the peer-reviewed journal Physical Review Research, this study introduces a sophisticated mathematical framework that quantifies the complex interplay between a quantum object's wave-like and particle-like characteristics. This breakthrough opens up exciting possibilities for advancements in quantum information and computing. Understanding the dance of wave and particle. Wave-particle duality is a foundational concept in quantum mechanics, illustrating how subatomic particles can exhibit properties of both waves, such as interference patterns, and particles, which have defined positions and paths. For decades, scientists have sought to quantify these dual behaviors. Earlier models represented this relationship as an inequality, implying that the combined wave-like and particle-like behaviors of an object could not exceed 1. While this was a valuable insight, it had a significant limitation. It allowed for scenarios where both behaviors could increase simultaneously, which contradicts their mutually exclusive nature. Dr. Xiaofeng Qian, an assistant professor of physics at Stevens and the lead author of the study, states, "For the past 50 years, researchers have aimed to quantify wave-particle duality, but this is the first comprehensive framework that accurately measures both wave-like and particle-like behaviors with optimal quantitative metrics relevant at the quantum level." The key innovation from the Stevens team is the introduction of a new variable, the coherence of the quantum object. Dr. Qian explains, coherence is a complex concept, but it essentially describes the potential for wave-like interference that is often hidden from view. By factoring in coherence along with traditional measures of wave-ness and particle-ness, the researchers established a precise mathematical relationship. When we account for coherence, we find that they sum to exactly 1, Qian adds. This elegant formula enables the calculation of wave-ness and particle-ness with unprecedented accuracy, moving beyond simple inequalities to provide exact values. Visually, this relationship can be represented as a perfect quarter circle for a fully coherent system, which morphs into a flatter ellipse as coherence decreases. From theory to practice, advancing quantum imaging. The implications of this new understanding of wave-particle duality extend far beyond theoretical physics. They have practical applications, especially in the fields of quantum information and quantum computing. To illustrate this, Dr. Qian's team applied their findings to a technique known as quantum imaging with undetected photons, QIUP. In QIUP, an object is scanned using one photon from an entangled pair. If this scanning photon travels through an aperture without obstruction, its coherence remains high. Conversely, if it collides with the walls of the aperture, its coherence diminishes significantly. By measuring the wave-ness and particle-ness of its entangled partner photon, the team could infer the coherence of the scanning photon and subsequently map the shape of the aperture. This demonstrates that the wave-ness and particle-ness of a quantum object can serve as valuable resources in quantum imaging and potentially in various other quantum information or computational tasks, Qian asserts. Remarkably, the researchers discovered that imaging could still be achieved even when external factors, such as temperature fluctuations or vibrations, compromised the overall coherence of the quantum system. Since these factors impact both high and low coherence scenarios equally, the critical differences in coherence between the two situations remain detectable. The ellipse may become squeezed, but we can still extract the necessary information about the object, Qian emphasizes, showcasing the resilience of their method. While this study marks a significant advancement, further exploration is essential, particularly in understanding how wave-particle duality operates in more intricate multipath quantum scenarios. As Dr. Qian concludes, the mathematics may appear straightforward, but we are far from fully unraveling the complexities of quantum mechanics. There are still numerous frontiers left for us to investigate. This pioneering research by the Stevens team not only enhances our fundamental comprehension of the quantum realm but also lays the foundation for transformative breakthroughs in quantum technologies. What are your thoughts on the implications of this research? Do you believe that understanding wave-particle duality could lead to even more revolutionary advancements in technology? Share your opinions in the comments below, ***.